Good afternoon to one and all joined here. We welcome this seventh day afternoon session of FDP. In this session, we have Dr. Vijay Ananth, Suyamburajan, Associate Professor, Wales Institute of Science and Technology and Advanced Studies with us. He did bachelor's in mechanical engineering in the year 2000 and completed his master's in 2002 from Ananth University and received his PhD in the year 2014 from Anna University, Chennai. He has published more than 30 international journals and conferences. Now, I would like to invite Dr. Vijayanand Suyamburajan to deliver his lecture. Sir, please, sir.
Good afternoon, sir. First of all, I thank you very much for our organizers for this faculty development program. Thank you so much. And now we will go into the session. Okay. Today we are going to discuss about the superplastic forming. It is a superplastic forming. It is one of a sheet metal forming process. With the help of the heat, we are making the components. Normally, in the room temperature, this metals having the very less ductility. Normally, aluminum have the ductility of nearly 10 to 12% of ductility only we can able to obtain. So to improve the ductility, what we are doing, we will heat the component as well as at the same time we are blowing the air. Okay, blowing the air. Due to the blowing of the air, the component will be formed as such the die shape. This is the main thing in the superplastic forming. And normally in this our stress strain diagram, up to the yield point we are having the elastic strength. After that yield point up to the ultimate tensile strength will have the formability ratio. From that only in the at room temperature these metals can be formed. As well as we are doing rolling or extrusion process in the room temperature process, which is done in between above the yield point and below the ultimate tensile strength. The same way for sheet metal also we are doing the same thing, but here in the superplastic forming, what we are doing, we are heating the component. Due to the heat, at the same time we are applying the air pressure. Sometimes we are using some of the dyes also to get the intricate shapes can be formed through that process. This is a superplastic forming process. Superplasticity. The superplasticity is a long neck free elongation under low flow stresses. And normally, while we are doing our tensile test with our UT machine in the normal condition, what will happen? Initially, this metal will become in the gauge region, it will make a small neck. After that, it will break, right? Normally, we have seen while we are testing our components in the UT machine, initial formation will be the neck formation. For the brittle materials, there is no neck formation will be there because there is no plastic deformation. So it will be failed at the time, right? But in the superplastic forming, there is no neck formation will be there. There is no neck formation. So due to the heat, the metal will be, the grains of the metal will be gliding one over another. So due to that, it will have the elongation of the material. That is what the superplastic forming. And normally we are heating the material more than 1/2 of the temperature, more than 1/2 of the melting temperature. Suppose the aluminum having 660 degrees centigrade means we will go ahead with 400 degrees centigrade. After more than 400 degree, we have to heat the component, then we will form the superplastic forming. But at the same time, this component should have this isothermal conditions, then only we can able to form the superplastic forming. Here we are having one example, lead and tin. And normally, suppose any material in the normal condition, we are having the elongation of maximum of 20% we can able to get. Otherwise, we cannot able to get the elongation. But here, lead and tin, and the maximum it is 7,550 percentage of elongation. So this much amount of elongation can be obtained through this superplastic forming. So depending upon the temperature also, as well as the strain rate. Strain rate means strain per second. Okay, how much amount of strain happening to the material, that is strain per second. So depending upon the strain rate also, this superplasticity is affecting, right? And normally this elongation already, when we are studying in the school time, we'll use this Aussie chocolate, right? After eating this chocolate, we'll have the cover. Two people will be pulling in the both the sides. It will be elongating, right? The same concept is applied in the superplastic farming setup, but it is in the hard condition. Hard condition. That is a main difference, right? Now we will go to the next slide. So normally in this two types of superplastic farming normally we are doing. That is, one is uniaxial farming, as another one is biaxial farming. The uniaxial farming, in the tensile testing machine we are doing. We are gripping this two ends. Then this gauge region is elongated. Okay, this is uniaxial tensile formation. Another one is biaxial. We are having the one die. The die we are fixing the sheet, right? This yellow color, which is the sheet. The bottom is a die. Now it is inside a heater, right? In a furnace, right? This die setup is in a furnace. You have to heat the die, and then afterwards we are applying the gas. And normally we are applying this argon gas, because oxidation will be there. Suppose we are using a normal gas, it will make oxidation of the material. So we are using the argon as a gas. So argon gas, it is passed inside. Then due to the pressure, what is happening? This sheet will be formed. So this red color is given as a formed component. Okay. So this is a superplastic farming, a basic superplastic farming method. The big history of superplastic farming, it is formed in 1964. It is Beckhoffen. He is a teacher of superplastic farming. Beckhoffen, he is formed the first bubble of his bubble in 1964. 1964, he has formed this bubble. Then 1965, Johnson, he has made the tube formation, right? And the tube is bended with the help of this heat, that is superplastic farming. That is Johnson by 1965. As well as in 1967, the zinc and aluminum based components were formed in 1967, and 1968 this door panels of the automobile industry, they have used that. Then after that, in the 70s we are having this machine. First machine of superplastic farming machine was developed in 1970s. Then from 75 to 95, many number of aluminum alloys, Supral 2020, Supral 5000. So many number of aluminum alloys has been formed through this superplastic farming method. The next one is General Motors. Normally they have formed many number of components with the help of this superplastic farming. Because they are General Motors, they are automakers, right? These automakers, they are using this superplastic farming, right? This is a lid which is used in the automobile industry of truck. The truck top body, which is in the cabin top, which is made up of with this superplastic farming with this aluminum of 5083 alloy. So this is a brief history of our superplastic forming process, right? The requirements of superplasticity. So what are the requirements for superplasticity? The main thing is grain size. And the grain size of this material should be less than 10 mm. Then the superplasticity can be obtained very easily. Suppose this grain size is very smaller, we can able to get the grain boundary sliding, right? The grains will be gliding one over another. We will see in the next slides the mechanism. So with the help of this when the grain size are very smaller, we can able to get a very good formation in the superplastic farming. So the grain size is one of the important requirement for superplastic farming. The next one is strain rate. We have already seen the strain per second. Okay, strain per second. And normally in this superplastic farming for smaller grain sector, we are doing with very small strain rates, very small. That is 10 to the power of -1 to 10 to the power of -5. So it will take more time. The superplastic farming will take more time. But at the same time, we are coming with metal matrix composites. Composite materials also can be formed through this superplastic forming. The strain rate will be 10 to the power minus 2 to 10 to the power of 0. So it is somewhat faster than that, because in this aluminum metal matrix composites, we are having the matrix as well as reinforcement particles will be there. And again, this reinforcement particles, it will may disturb the flowing of the grains. So for that, we are having second phase particles will be there. We will see in the next step, we will see that. Okay. So this aluminum metal matrix composite, the high strain rate is required for this metal forming process. Then the temperature, already we have discussed, the temperature should be more than 1/2 of the melting point, right? Suppose for the aluminum, we have to heat the component more than 400 degree. More than 400 degree, we have to heat the component. Then we have to wait for the isothermal condition should be obtained all over the surface of the component. Then only we can able to get the superplastic forming. So this is for temperature. Then as well as the grain shape also playing an important role in this superplastic forming. Equiaxed grains, it will be very much useful for superplastic forming. The equiaxial grains means the width as well as height of this grain should be equal, right? That is called as from the axis, all the sides should be equal. Then this formation of superplastic forming, it will be very good, right? So this is a that is 10 micrometer. Is not 10 mm, 10 micrometer. Then presence of second phase particle. What is a second phase particle? Suppose in a for alloy elements, we are having a second phase, right? For aluminum 6, aluminum we are having more number of series will be there, 2000, 3000, right? 5000, 6000 up to 7000 series also there. For example, in the 6000 series, we are adding magnesium and silica, right? Magnesium and silica were very small percentage, it is less than 3%. We are adding this. So what will happen? We are heating the component more than 400 to 500 degrees centigrade. What will happen? The second phase, this magnesium and silica, it is melted, right? It is melted. It is not fully melted. It is like a very thick metal. Just it is starting to melt. So it is very much softer. So the second phase, Mg2Si, it will form. Magnesium silicate will be formed as a second phase part. Second phase. So what will happen? While the second phase is there throughout the grain, so the grains will be moving very easily. It is reduce the friction between the grain, so it will improve the formability of the material. So this is the main requirement of the second phase material, second phase presence in the superplastic form. Understand, no? Right. The next one is a grain boundary shape also. Suppose very large angled grains, it will reduce the superplastic forming. So the large angle should be, it should not be there. Very short angle is very much useful for superplastic forming, right? The next one is types of superplasticity. So we are having different types of superplastic forming. The first one is fine structure superplastic forming. This fine structure superplastic forming, already discussed, the grain size should be very less than 10 micrometer. 10 micrometer means we'll have that is called as fine structure superplasticity. For ceramics, it is requirement is 1 micrometer. For ceramic material, the grain size should be 1 micrometer. So the fine structure superplasticity, the grains will be sliding one over another. So grain boundary sliding is the main mechanism to form in the fine structure superplasticity. The next one is internal stress superplasticity. Internal stress superplasticity. In this internal stress superplasticity, when we are very much aware of this creep test, right? We have seen how the creep test is made for the material, right? This internal stress superplasticity testing also doing with this our creep testing machine. What we will do in a creep testing machine, we are having the furnace. Inside the furnace, we are fixing the component. The bottom, we are having the load. The top end is fixed. The bottom end, we are having certain load we are having. Then we will do the creep test. But here in this internal stress superplasticity, what we will do, we will heat the component as well as we will reduce the temperature also. Suppose we are for aluminum, we are heating up to 450 degrees centigrade for the testing. Then again reducing the temperature about 300 degrees centigrade. This 150 degree, we are heating and cooling, it will be happening. It is a cyclic process that is called as thermal cycling process. So due to that thermal cycling process, what will happen? While we are heating the component, during the heating, this component will be expanded. And again, when we are cooling, automatically the components will be shrinkaged. So due to that, what will happen? The shrinkage and as well as expansion takes place in the material. Due to that, it will have some stresses inside. The stresses will be formed in this components. Due to that stress, it is increasing the elongation. That is called as a internal stress superplasticity, right? This is a ideal Newtonian viscous behavior. This Newtonian viscous behavior means normally in a Discovery Channel also you have seen, right? The glass formation, the glass Arctic arts were made with the glass. You have seen they will heat the glass material and they will change into different shapes, right? The glass material. The ideal example for superplastic forming is the glass material, right? Glass in the glass only this Newtonian viscous flow will be happening in the grains. So the grains will be moving very freely, right? It is already we have seen this. They are changing the shapes of the glass in a higher temperature. Very intricate shapes can be formed through that. So that is a Newtonian viscous behavior. The best example is a glass material. Okay, glass material. The next one is high strain rate superplastic forming. It is about 10 to the power minus 1 to 10 to the power 1. So forming time will be reduced significantly due to that high strain rate superplastic forming. Due to that, because it is the formability is forming is very much faster compared to other methods. Mainly the second phase already we have discussed. This second phase playing an important role in this high strain rate superplastic forming. As well as I have already told, for the composite materials also will have a second phase. We are having the reinforcement will be there. Suppose in the metal we are having silicon carbide particles will be there, means the silicon carbide particles it will not disturb this grain movement with the help of this second phase particle. So this is a high strain rate superplastic form. These are all the three types of superplastic forming. The superplastic forming equation, it is sigma is equal to k epsilon dot power m. Sigma is a true stress and strain rate, k is a strength coefficient, and m is a strain rate sensitivity index. The strain rate sensitivity index is playing an important role in the superplastic forming. It is a main requirement. Minimum a material should have m value of 0.3. So the maximum value of 1. So the glass material which is having the m value of 1. So already I have told, no, this ideal material for superplastic forming is a glass, right? So glass having the m value of 1. But the minimum requirement should be 0.3 to 1. And normally our aluminum alloys having the m value of 0.5 up to nearly 0.5 to 0.6 we can able to get. So it will obey the superplastic forming, right? So that is what here there is a Newtonian. Suppose m is equal to 1, we'll have the Newtonian viscous flow we can able to get. It is a completely neck-free elongation. Okay, there is no neck formation will be there. So continuously it is in the grain boundaries are continuously moving. The grains will be moving, right? So we'll have a very high elongation can be obtained through this while the material having m is equal to 1. The strain rate sensitivity index, where suppose we are having 1 value, it is a high elongation can be obtained. This is a superplastic forming flow equation. And now you know about this creep curve, right? In this creep curve, already we have studied, right? Here, the initial region, what will happen? Initially, the temperature, sometimes initial flow, it is elongation of grains will be there, right? The elongation of grains. Once this, while we are doing this forming process, suppose we are doing the rolling, extrusion in the room temperature, what will happen? Normally, these grains will be elongated due to the applied force. What is happening? It is changing the shape and it is elongated. So in this first region, this grain structure it is changing. It is elongated. The the structure is elongated, right? This is the first region. The second region only we can able to have this superplastic.
Vijayan sir,
Yeah.
you can increase your audio, sir. Audio.
Okay.
The system, you can increase the audio.
Now you can able to hear, no? Right? Now it's clear?
Yes, sir. Yes, sir. Yes, sir.
Okay, right. So in this second region only we will able to get the zooplastic forming capability. So here this grain boundary sliding, Newtonian viscous flow, everything will be happening in this second region. Okay, so in this region only we can able to get this m value of 0.3 to 1. We can able to get only through this region, right? So that is what they have given the strain rate sensitivity index versus strain rate. We are having the curve. So this is a value we are having more amount of m value we can able to obtain. So here we are having the maximum it is in the higher temperature as well as fine grain size materials can be obtained this higher m value. The last region automatically it is in the failure region, right? So it will be at last this component is going to fail. So it is the components will be failing. So the grains will be breaking region. But here the grains are moving one over another. The grain boundary sliding can be obtained in this region, as well as this exchange of grains also takes place in this second region. The mechanism behind the superplastic forming. There are 5 mechanisms are there, right? Grain boundary gliding, dislocation movement, exchange mechanism, permutation model, and mechanism of creep. We'll see one by one. Grain boundary gliding. So in this grain boundary gliding, what will happen? This neighboring grains are automatically move one over another. Okay. Sometimes what will happen? These grains also rotated themselves depending upon the load applied. Suppose we are having the tensile load is applied. Due to the load, what will happen? The grains will be moving, and the gauge region, what will happen? Automatically, the grains will be moving there. Sometimes what will happen? Here, what will happen? Exchange of neighboring grains also takes place. Sometimes these grains will be rotated themselves. So due to that, we will get the elongation takes place in the material. This is a grain boundary sliding mechanism. The next one is gliding of dislocation. So normally in a grain structure, uniform grains will be there. Sometimes what will happen? Some grains will be sliding one over another. Here some dislocations will take place. So due to that, what will happen? Some more stresses will be induced on that area. And here then the slips will be takes place. And due to the slipping, what will happen? This grains will be slipping, and sometimes it will lead to some of the cavitations also formed. Cavitations means some empty spaces will be there, right? So these cavitations lead to some of the failure in the components will be takes place. So it will lead to sometimes in the cavitation, but in the slips, and again these grains will be moved, and it will be exchange the grainsment, and automatically again it will replace its own. Okay, so this is a grain gliding of dislocation. The next one is the exchange of mechanism. The exchange of mechanism, we can the best example is soap bubbles, right? In water, suppose we are having the soap bubble. Suppose we are touching the soap bubble, it will not break, right? It will be, suppose the soap bubbles will be moving one over another very easily, right? So here initially this is a arrangement of the first diagram. We are having this arrangement of ABCD. It is a grain. The second, now we have during deformation. Deformation itself, the movement of grains will be taking place, right? So here the AB, D, and again the D is moving upward direction. Again the stage 3, further more deformation takes place. Again this ABD takes place. Again the K is moving here. So the grains are moving as like the soap bubbles. How the soap bubbles are moving from one place to another while we are applying the load in the material, the grains are moving as like the soap bubbles. This is a exchange mechanism of superplastic forming. Next one is permutation model. In this permutation model, it is very well explained, right? So the load is applied, the tensile load is applied. The grains are 4. We are having 4 grains will be there. Now we are applying the force. Due to that, what will happen here? This compression force will be takes place, right? While we are here, the two sides we are pulling the material. So here some compression takes place. Due to the compression, what will happen? This second grain, the 2 grain will be moving in upward direction, and again this 4 is moving here downwards. This 1 and 3 is coming together. So it is the deformation takes place in the longitudinal manner. So plastic forming takes place in the longitudinal manner. At the same time, what will happen? This is called the diffusion. Diffusion means this grains will be rotation. Grains rotation movement, it is called as a diffusion. So due to the rotation movement, diffusion takes place. So from that we can able to get the elongation in the superplastic forming. This is a permutation model. The last one is a mechanism of creep. And again, here we are applying the tensile force in up and downward force. So what will happen? Automatically, here while we are pulling this material, some cavity it is takes place. Some cavitation or some vacancy it takes place. So due to the vacancy, what will happen? When the vacancy takes place, one donor will be there. So the donor and the vacancy, so these vacancies are filled up with the donor grains. So due to that, will form the superplastic forming will takes place. This is a mechanism of creep formation. The next one will see what are the materials can be formed through superplastic forming process. The materials are crystalline materials, ceramics, metal matrix composites, as well as intermetallics. So these are all the materials can be formed in this superplastic forming. And again, some of the materials we cannot able to form through these conventional methods, right? Suppose taking example, magnesium. Magnesium, it is a brittle material, right? Our composite, metal metals composites also a brittle material. In the normal forming process, what will happen? Suppose we are doing the forming process, what it will lead to some of the cracks will form. We cannot able to form the perfect component through this process. But in superplastic forming, that materials can be formed very easily. Okay. Right, like that in ceramics also is a very brittle material. This brittle materials also we will have the by superplastic forming process we can able to form the component. So this first metal is a tensile specimen which is elongated. There is lead and tin. Okay, tin and bismuth. It is elongated this much length. Already we have seen in the first slide. It is nearly 7,000%, nearly 7,000% of elongation. So this metal also having this 7,000% of elongation can be obtained in the metal. In the normal forming, normal conditions in the room temperature, the material maximum elongation of 20% or 20 to 25% only we can able to get. But in superplastic forming, we can able to get more than 7,000% of elongation can be obtained. This is ceramic part which is having the elongation, right? This is a original specimen. This is the elongated specimen. The same way, the last one is silicon nitride, silicon carbide, composite ceramic material. This is also having this much amount of elongation, right? So by superplastic forming, in the material difficult to form by conventional process can be formed through this superplastic forming process, right? Now aluminum alloys. Aluminum alloys are playing a vital role in the aerospace industry, right, as well as space programs. So for that forming, very much superplastic forming is very much useful for in the aluminum alloys. And normally the aluminum magnesium manganese alloy, which is very much useful in the automobile parts, in the mass production of sheets also can be obtained. It is having more than 300% of elongation at the temperature of 540 degrees centigrade. 540 degree centigrade. Aluminum lithium based alloys very much useful in the aircraft and aerospace industries. It is having the elongation of 600% of elongation with the 600 to 850% of elongation can be obtained in this material, aluminum lithium based material, and again it is having the density is very less. So density is less means automatically this metal having the very less weight, so very much useful in the aerospace as well as in the aircraft industry. And aluminum, zinc, magnesium alloys, it can also form up to 3250% of elongation obtained at the temperature of 535 degrees centigrade, 0.01. There is a high strain rate, right, at -2, -2 per second. So very high strain rate it is obtained at elongation of 3250. So these are all some of the elongation capabilities and the temperature. How much temperature for different alloys is given. So aluminum, zinc, and zirconia at 900% of elongation obtained at the temperature of 480 degrees centigrade, right? 480 degrees centigrade. Another one high elongation, it is aluminum, magnesium, silica. It is 6000 series, aluminum 6000 series, aluminum, magnesium, silica. It is at 530 degrees centigrade. You'll have the higher elongation, as well as this magnesium, silica, zirconia. So from these different temperatures, as well as each alloy having the different temperature behavior for superplastic form. That is what we have seen through this graph. The titanium alloys. The titanium alloys are a very high strength to weight ratio, right? High strength to weight ratio. So this is very much useful in this aerospace industries. These are all some of the alloys we are having. It is having higher percentage of elongation. Nearly this titanium 4Al and 4MO and SN silica alumina alloy. That is IMI 550. It is having 2000% of elongation, as well as the next one SP700, which is having 2500% of elongation was obtained, as well as we are having the strain rates also, right? Very slow strain rate. Some of the materials having very slow strain rate. Some of the alloys having a very high strain rate. And normally at the higher temperatures, we are having the very high strain rate is takes place, right? As well as intermetallic based alloys also formed in this titanium based alloys formed with superplastic forming. The last one, the titanium based composites, titanium and titanium carbide, titanium plus titanium nitride composites also formed by superplastic forming. The elongation was obtained about nearly 410%. 410% was obtained at the temperature of 920 degrees centigrade. Next one, magnesium based alloys. Magnesium alloys are very light weight. Normally nowadays very much useful in aerospace as well as in automobile industries. Automobile drivetrains now we are using in the automobile engines also. Nowadays we are using the magnesium. So this magnesium can be magnesium materials are formed through this superplastic forming. Here AZ61A, which is having 600% of elongation at a lower temperature of 290 degrees centigrade, right? As well as ZK60A having the elongation of 700% at the temperature of 310 degrees centigrade. Right? Sir, am I audible, sir? Right?
Yes, sir.
Okay, right. Now we are comparing the density of steel. It is nearly 7.8 and aluminum 2.65, and magnesium density is 1.78. So very less density. So automatically it is much useful for any automobile components. It will be reducing the weight automatically. Will have the higher efficiency of the vehicles. So very much this magnesium superplastic forming is nowadays it is going on. Let us more and more number of components are formed through this superplastic forming, right? This is a component for it is a inner door. A car inner door. It is a trial based. It is formed. Inner door is formed through this superplastic forming of magnesium alloy. Iron-based alloys also formed through this superplastic forming. It is reported in 1997, and the plain carbon steels have obtained 1000% of elongation. 1000% elongation at 800 degrees centigrade at the strain, a very slow strain rate of 10 to the power of -5 to 10 to the power of -3. Right? Many steel alloys also formed through this superplastic forming process. As already we have discussed, the aluminum metal matrix composites also can be also formed through this superplastic forming. Mainly, this composite materials normally it is behave like a brittle material, right? Due to this reinforcement component in the material, this ductility will be very less. So these materials can be formed as a useful component through superplastic forming. Superplastic forming. Many literature has been reported that silicon carbide whiskers, they are using the silicon carbide whisker instead of particles. They are having the whiskers. This silicon carbide whiskers, they are having the elongation of more than 500 to 600 percentage of elongation can be obtained through this superplastic forming process. As well as we are having this using silicon carbide particles also, but in silicon carbide whiskers we are having, it is like a short fiber, so it is having very high elongation as well as very good properties for this aluminum metal matrix composites. As well as this nickel based alloys very much used in this jet engine parts. It is used in this compressor and turbine discs and rings which are all formed in this through this nickel based alloys. These fasteners are made up of with superplastic forming, right? This the superplastic forming we can able to get more than 700% of elongation we can obtain through this process at the strain rate of 1.33 minus 10 to the power of -5, very slow strain rate. Okay, nickel based alloys. Ceramics also formed through this superplastic forming. Here they have given Al2O3 and OEDZ ceramics, which is formed at different timings they have given. It is with the 15 minutes and 125 minutes with a higher temperature with a pressure of 13.8 megapascal. Pressure of 13.8 megapascal we can able to form as a formed ceramics. Whether in normal conditions, conventional models, we cannot able to form this type of components, right? Because surely it will break. It is very much brittle material, but only with the help of superplastic forming, these ceramics can be elongated this much percentage. The same way, this bulk class zirconia titanium combined form of ceramics also formed through this superplastic forming. So ceramics also can be formed through this superplastic forming. The main advantage of superplastic forming, that is complex and intricate shapes can be formed, and the capital investment cost is very less, right? Compared to some other conventional machines. We need one furnace as well as with one compressor with the argon gas cylinder as well as one die. Within this setup, we can able to form a superplastic forming. So the capital cost of equipment is very much less. Brittle materials can be formed easily, formed through this superplastic forming, right? And diffusion bonding also can be formed through this superplastic forming. We will see in the some slides are there. There I will explain about this. There's a diffusion bonding, right? So it will reduce the fasteners, right? Fasteners we can attend mold and again we are welding. It will also add some of the weight to the components. So we have to reduce the weight, mean automatically this number of fasteners and secondary operation should be reduced. So for that, this is very much useful. The superplastic forms are very much useful, right? And this fine grain size automatically, the fine grain size means automatically ductility will be more fatigue strength will be there. So normal properties also improved through this superplastic forming. Low cost tooling already we have discussed. And again, we are not using any lubricants, right? There is no noise will be there in the superplastic forming. So these are all the main advantages of superplastic forming. Some limitations: it is a very slow process and very slow speed is very limited, right? And another one thing is very expensive in the pre-forming setup. To get the fine grain size, we have to do some heat treatment process as well as some of the rolling process we have to do. So it is somewhat it is expensive to for the pre-forming process. And again, we are having a very limited records of the deformation failures are available in the superplastic forming. So these are all the some of the limitations of the superplastic forming. Next, we will go to the applications in the superplastic forming. In applications, this is an aero engine. Aero engine, actually, in the aerospace industry, more than 2,700 components has been formed through this superplastic forming. More than 2,700 components are formed through this superplastic forming. These are some of the examples in the aero engine parts which are all formed through this superplastic forming. That is top core, the panel, inlet rings, compressor blades, inlet cone. That is inlet cone. There is oil tanks. Okay, dovetail seal. So these are many components. The exhaust nozzle. So these structures, right? The cube-like structures, which is formed through this method, is very easy, right? So that type of components are formed through this. Aerospace components are formed through this superplastic forming. These are some of the applications of their superplastic forming in the aerospace structures, right? Lid skins, bulkheads, lamp drums, which are all made up of this superplastic forming. Access door inner skin. Already these door inner skins are very much used in automobile industries also. The equipment covers, acoustic panels, which are all made up of this. These are all the components which are all made up of this superplastic forming process. This is an example for diffusion bonding of titanium alloy. Okay, diffusion bonding. It is by this company Dassault, which is made this component by this superplastic forming process. Okay, this is two sheets. So one is bottom side and one on upper side. So these two things are made up of this superplastic forming. We are having the die, so top and bottom, and we are applying the air. Due to the air, it is formed, as well as the diffusion bonding also takes place in the two sheets. Right, this aerospace industry, and again, this is the exhaust cone, which is made up of with superplastic forming, and the fairing flaps. We have seen by this wings of the plane, where the flaps will be there. These flaps are in the batch process. We have made this flaring flaps are made with batch type forming in the superplastic forming. We have formed, as well as these blades, fan blades. Fan blades are made up of with superplastic forming, as well as the piping grids, which are all made up of with superplastic. These are all the titanium-based alloys. Which are used in this aerospace industry, which is made up of with superplastic form, right? And then this automobile industry, door inners, body sides, door inner rings, and tunnel pinners, and then the structures. Total structures also can be formed through this superplastic forming, as well as exterior body. Exterior body components also formed through this superplastic forming. Foot walls, when they are replacing the foot spaces there, no, that space also can be made through this superplastic forming process. Then art gallery materials like structures also formed through this superplastic forming, right? This bicycle frame. This bicycle frame is made up of with this superplastic forming material, right? Then this is chair. Okay, a chair, the furniture, which is this top portion. The top portion, which is made up of with this superplastic forming material, right? The superplastic forming process. And the railway, right? In the train, many components are made up of with superplastic forming. That is cap skin, cap structures, inner end skin, inner end canopies, right? Cab interiors, door systems. There's so many components which are all made up with the superplastic forming. This is a component which is a high pressure vessel, which is made up of the titanium alloy, which is laser welded. The top portion and bottom portion is separately formed, and it is welded with the laser welding technique. And here spherical coolant containers, which is used for infrared detectors. This is also titanium based alloys which are all formed through these methods. Then hemisphere of a submarine part, it is having a 400 mm diameter, right? The diameter is 400 mm diameter, and the thickness is 20 mm. The plate thickness is 20 mm thickness. Also, it is a titanium alloy, which is made up of the hemisphere of the submarine, which is formed, as well as some of the medical implants. Also, it is used. The titanium alloy, which is used in the helicopter cover component, and aircraft housing, which is also made up of with plastic forming with the titanium alloy. And another one is this missile nose components, which are also made up of with plastic forming techniques. And again this face recognition, face structure, as well as implants in this dental work also can be done with this plastic forming. So these are all some of the applications, as well as high diameter to wall thickness ratio. With this very less thickness components also can be formed, like a dome like structure can be obtained through this plastic forming. So these are all the components which are all made up of this plastic forming, and that is the thickness is from 0.5 to 25 mm, right, as well as the diameter of 50 to 760 mm diameter components also formed through this plastic forming. The materials, titanium as well as chromium nickel alloys, already we have discussed, right? So here there is no residual stresses will be there, no spring back effect, right? And tooling is very much cheaper, right? So these are all the some of the applications in the plastic forming. The main another one advantage in the plastic forming, diffusion bonding also can be done through this plastic forming. The normal diffusion bonding process, what we will do, we will have the two sheets will be there. We will have the high pressure is applied in the top and bottom of the plates at the furnace, then it is formed. But here we are only applying the air pressure. So normally in the normal condition, then while we are applying the pressure conditions, then the diffusion takes place. These atoms are replaced with each material. So due to that, this forming diffusion is takes place. So these things will happen in the plastic forming in a single process. Okay, this is titanium and steel diffusion bonding through this plastic forming component, right? They are having the uniform structures has been obtained due to the diffusion bonding process. The applications, low thermal expansion coefficient, and the material will become low thermal expansion coefficient, very good friction resistant component, and as well as it is very much hardness, as well as very much corrosion resistance. Now we'll have one video regarding with plastic forming, how these components are made in the companies, right? This is PDF. I cannot able to play that video, right? At last I will play that video, right? I have converted this into PDF, so I cannot able to play. At last I will play the video. And now our FDP program is based on the composite material. Now we will see one how this aluminum silicon carbide based composites are formed as a plastic forming. We'll go through that. Now we will go through that. Now initially this aluminum 6063 silicon carbide component, which is composite, which is made up of the stir casting process. This is a furnace. This is a crucible. The crucible, this metal is poured, and as well as SiC particles which are preheated. The preheated silicon carbide particles are poured inside, and then this is a stirrer, right? This is a stirrer motor. Continuously it will stirring it. So this is a grain size of average grain size of silicon carbide particles, uh, which are used near normally less than 10 micron size, right? So normally to prevent some of the procedures we will do. So we are putting some of the D gases to remove the waste gases, as well as some put nuclear tablets to refine the grains, as well as some of the, these are all the things we will put in the top surface. So while we are putting this in the top surface, what the coverall, what it will do, the oxidation will be prevented. So through that process, we are stirring process, we are making the composites. These composites were casted the 100 cross 5 thickness plates, right? Then it should be, I have already told, we have to do some pre-processing for the materials. Pre-processing is required for superplastic forming. So further, we are doing the solution treatment for 521 degrees centigrade within the furnace for 1 hour. Then it is water quench. Then we are doing the warm rolling, 300 degrees centigrade. We have rolled the cast component, and we have reduced the thickness up to 2.5 mm. 2.5 mm thickness we have reduced. Then we are doing the natural aging for 3 days. After that, we are making this. This is a rolled component. This is a rolled component. The rolled components are circularly cut as a required for our die shape. So this is these circular shapes are cut through this rolled component. And then this is a setup. This is a superplastic forming setup, which is it is in the MIT campus. We are having the superplastic forming die setup. It is a split type furnace. This is a die. This is a die. This the die bottom, which is connected with the pipe, which is connected with the compressor, right? Compressor. And again, we are having one temperature controller to control the temperature of the furnace, as well as LVDT. This LVDT is mainly used to measure the formation. How much amount of this cone formation will be, the cup formation will be takes place. Each and every 10 seconds, we will note down the details and we will record the value, right? So this is a setup for superplastic form, right? So what will happen? We'll fix the component and we will close, and we will first initially we have to heat the setup for half an hour to reach the temperature about 540 degree, 550 degrees centigrade record temperature. Once it is reached, and to reach this isothermal condition, once again we will maintain that temperature for another 15 minutes. Once it is reached for this temperature, then we will open this air. Okay, when we will open this air, while this open this air, automatically this bulge formation will be takes place. We will go through that, right? Dome height. This not on through this LVDT. Okay, LVDT. Normally, once initially open our air, initial formation will be very much higher. So initially this air is touching this component. So the first 6 mm it is formed very quickly. Then it is step by step, nearly 2000 seconds, right? 2000 seconds we are making this component. Here we are having three different types of composites. One is 5% and 8% and 10%. We are following the same procedure. We are casting the component and rolling, and the solution treatment, rolling, and the natural aging process. Then we are cutting the component. Then we are testing in the superplastic forming center. So this 10% of silicon carbide, which is having very less height is obtained. Nearly maximum 10 mm height is obtained in this process, and 5% we are having the more height is obtained through this process. H by D ratio. H by D ratio is one of the important parameter to whether this composite is behaving with superplastic forming or not. We can able to find through this process whether any material which is having more than 3 of H by D ratio, then it is having the superplastic forming capability. So this 5% of 5% silicon carbide composite, it is having the very good superplastic forming capability. By this test we have obtained. That is a H by D ratio. H by D ratio means height to the diameter. Height is the forming cup, the cup forming die height. Then it is divided by the diameter. Okay. So this H/D ratio should be more than 3. Then only it is taken it as a superplastic forming capability. Here we are using 3 pressures, 0.2, 0.4 and 0.6 megapascal, right? This 0.6 megapascal higher pressure we are having, higher formability we are getting here, right? This is to find out the stress and strain value. We can find through this process biaxial superplastic forming. The stress sigma 1 can be obtained by this pressure and radius of curvature divided by 2 in S. S is the thickness of the sheet, thickness of the final thickness of the sheet. So from that we can able to get the stress value as well as the strain value. Okay, strain value, that is change in thickness, right? S by S0. This is a S is the final thickness, dome thickness. This is the initial thickness SO. So from that we can able to get the strain value as well as we can able to get the instantaneous strain. So from that we can able to put the plot the graphs. So from that we have plotted the graph. That is this is the time as well as the dome height for different temperatures. Different temperatures we have tested. 560, 580 and 600 degrees centigrade. At this 600 degrees centigrade, what is happening? We'll have very high percentage of elongation, but it is the components are failed at the end. If the components are failed within a very short period, these components are failed. But other components, this 580 degree and 560 degree, the components are not failed, but we are having the forming nearly 19 mm of dome height is obtained. Right. This is a dome for the, and again the high pressure also. This is in the 0.6 megapascal. For 0.4 megapascal, this component is not failed. Okay. Again, this is also failed. This at 600 degrees centigrade. These components also failed at this time, but other two components not failed. So while the higher temperature, this components are failing. So we have the optimum temperature to get a superplastic forming in aluminum 6063 silicon carbide composite, it is 580 degree. So 680 degrees centigrade, many times it is failed. So but in very good forming is obtained through this 580 degree centigrade. So these are all the some of the formed components. Already we have shown in the graph, right? At 0.2 megapascal, this is 0.2 megapascal with 600 degree, 580 degrees centigrade and 560 degrees centigrade. This is for 0.4 megapascal and 0.6 megapascal. The 0.6 it is failed when we are having small size hole circle, right? So air will be leaked through this. This is a so this is a component, failed component. This is also a failed component. Now already we have initially discussed about the strain rate sensitivity index. The main requirement for strain rate sensitivity index should be 0.3, right? We should have a minimum 0.3. So at 600 degrees centigrade we are having very good formability, but still this 0.2 is obtained in the 580 degrees centigrade and 560 degree is 0.1. This is for 0.6 megapascal. The same way we have calculated for 0.4 as well as 0.2 megapascal also. The 0.4 megapascal we are having a very good formability, and again we are getting this M value of nearly 0.345. So more than 0.3 we are getting for this composites. Then the thinning factor. So while after forming this component, we can able to check the thickness variation around this component. So by digital height gauge, we can able to find the thickness of the component. The thinning factor also we can able to form. The thinning factor is T by T average thickness at the point as well as the average thickness of the fold dome, right? And thickness strain also we can able to calculate by T by T0 with the formula we can able to calculate, right? So these are all the places we can to get the average thickness. So average thickness, all these places we have found the thickness. Then we are taking the average, right? Initial thickness to the thickness average. We can, from that we can get the thinning factor. So these are all the thinning factors we have obtained at the 0.2 megapascal. These are all the thinning factors at the points that these angles, that 30-degree angle, 60-degree angle, we have plotted. This is the pole region we are having less, the thickness will be very less. The same way for thickness in the 0.6 megapascal, at 600 degree, more thickness will be there. The thickness is reduced nearly 1 mm. The initial thickness will be 2.5 mm, but the final thickness at the pole region is very less. So it is leading to the failure, right? This is a thinning factor. So these theoretical thinning factors we can calculate through the Excel sheet for the different temperatures as well as the different pressure values, right? These are the thinning factors. And again, to find this strain rate sensitivity index, strain rate M, I have already known sigma is equal to K epsilon power M. This M is playing a very vital role for any material, whether this material is behaving superplasticity or not. So for that, we are having another one method. This is biaxial superplastic forming, that is multi-dome test. Multi-dome test. We are having the diameter of 2 mm, 5 mm, and 10 mm diameters. 2 mm, 5 mm, 10 mm diameters. Already we have seen the setup. In the setup, this sheet also fixed into the die. Then the components is used for the bulging operation. So from that we can able to calculate the strain value and the stress value. So from that we can able to calculate the strain rate sensitivity index. One is through the graph uniaxial tensile strength. We can able to calculate the strain rate sensitivity index. Another one method is through forming through the multi-dome test. So these are the components formed by multi-dome test. So this is a height, dome height we have obtained, as well as the thickness, strain, stress. So for different temperatures, we have calculated the strain rate sensitivity index. And again, this 600 degree, we are having the maximum strain rate sensitivity index we have obtained, right? So in the uniaxial tensile test also, we are getting this high M value through this process. 580 we are getting nearly 0.25, right? 0.25, 560 very less. So more than 580 degree centigrade only this material is behaving super plasticity. So these are all some of the microstructures we have obtained after forming this superplastic forming at the dome. We have obtained. It is a composite, right? Composites. These are all the grains. Silicon carbide particles also we have seen through that. This is in the 580 degrees centigrade. So these are this is a grain size, right? These are all the grains, right? Very good forming obtained in the 580 degrees centigrade. At 600 degrees centigrade, I have told no, these components were failed. So very micron level cracks were found in the grain boundaries, right? So these are all the failures. So these are all the small failures we are obtained through this some microstructure, right? In the grain boundaries, mainly in the grain boundaries which are all failed, right? In the 600 degree centigrade. So this is a difference between normal in at room temperature when our composite failed at as well as which is failed in the superplastic forming at a higher temperature. So this is in the normal temperature. So very brittle in nature. It is failed in the very brittle nature. Only dimples are seen through that. But here in the superplastic forming, it is having a very ductile fracture. It is takes place, right? Very small whiskers are found in this microstructure, right? So this is a superplastic forming failure, right? This component is failed through this superplastic forming. So each and every, this is a grain boundary failure. So this is one boundary, this is another one boundary. So this boundary, the component is failed in this grain boundaries. It is very much visible through this diagram, right? And the next one we have done with the hot tensile test. There is a one furnace, a spread type furnace. We are having the specimen is Inside again we have increased the temperature. We have done the test with different strain rates, right? With a constant different temperature with constant strain rate. Constant strain rate. These are all the specimens we have used, right? At 520, 25% elongation. 540, 75% of elongation. At 560 degree, we are having 150% of elongation. 580, nearly 225% of elongation. So maximum elongation is obtained in 580 degree centigrade. At 600 degrees centigrade, the components are failed very quickly. Very quickly, it is failed. So these are all the graft obtained through this UTM machine hard tensile test. So this is 520 degree, 520 degree, very true stress versus true strain rate. So this is a component we are having very high formability at 580 degree, 580 degrees centigrade. We are having a very good formability. Very good formability can be obtained. This is a true strain value. This 520, there is no not much strain takes place in this thing at 520 degrees centigrade. Now we have seen some of done the very good microstructure analysis. What is happened through this hot tensile test during the superplastic forming. We have taken this microstructure from these parts. This is A, B, C, D, E, F, right? And we'll see how this microstructure is changing through superplastic forming, right? So this is some micrograph. These are all the grains, as well as in the grain boundaries only we are having the silicon carbon particles, as well as second phase particles also there, the Mg2SA like that, right? So these are the grains, right? And this is in the gauge region. This is also in the A is a gauge region, B near to the gauge region, B near to the gauge region. From here only this deformation takes place from C. As C, this is a C. Some small changes takes place here. Small, some movement of grains we can able to see here. The D area we can able to see many subgrains are formed during that process. Right? It is very much visible here. You compare this A and D here. Very many number of small subgrains are formed due to this pulling of our pulling this tensile load. This small grains are formed right in the D region. Now E and F, this in this M area. Now we can able to see these grain boundaries are moving right in a axial area, right? In that area, you can able to see all the grains are moving through that area, right? Many small subgrains are formed, right? At the end of failure, some of the grains which are all elongated, but many grains which are all in the same structure, right? Maximum we are getting the UK grains we are obtained, right? So this is grain structure changes during the superplastic forming. So initially we have seen the mechanism, right? Grain boundary sliding, these things we have seen. So by here the very good flow of grains through this material we have seen through this microstructure, right? So these are all some of the components we have formed components, right? Very less height was obtained in the 520, 580 degrees centigrade. And this is this component, the cut shape of this components. The 600 degrees, some of the components failed in this edges, right? At the high pressure, 0.7 megapascal. Initially, we have tested the trial and error method. We have tested many components, right? So these are all the test superplastic forming conducted in aluminum 6063 silicon carbide composites. Some of the research perspective, we can able to do this in the superplastic form is the cavitational behavior of superplastic forming. It is a wide area, more gap is there to how to get the cavitational effects of superplastic forming. Another one area, pulsed current superplastic forming. Now it is in the research work, and this some of the induction currents are used. Pulsed currents are used to form the components. So due to that, more elongation will be there, as well as it is reduction in the failure, as well as the component elongation is more in this pulsed current superplastic forming. Forming, that is also one research area we can able to concentrate. And the last one, there is already I have told pre-processing is very much necessary for superplastic forming. So for that, for grain refinement techniques, we can able to for optimizing the grain very minute grains by friction state processing. One of the latest technology nowadays. Now they are using from 2015 5 onwards. They are doing this friction state processing. After the friction state processing, they are doing the superplastic forming, right? So due to that, due to that friction processing, these grains are very much smaller grains we can obtain. Up to 1 micron size we can able to obtain through this friction processing, as well as for the composite materials, this our reinforcement particles can be once again rearranged and distributed all over the matrix can be done through this friction state processing. That area also we can able to do more work through this friction state processing. And e-capping process, another one process, it is also used to reduce the grain size, right? Grain size. So by reduction in grain size, automatically we will get a very high elongation can be obtained through this superplastic forming. So these are all the areas we can able to do research in this superplastic forming, right? So this is the end of the session. Thank you very much for your patience by listening my lecture for last 1 hour, right? Thank you so much. Now we will open for the queries. Any queries we are having? Now I will explain the queries. Thank you.
Sir, I am Ram Gopal Reddy from RVRNG's College of Engineering, Andhra Pradesh. Hello.
Yes, sir. Yes, sir. Yes, sir.
Sir, is there any criteria at what temperature the material must be heated in order to have this superplastic forming? So that is so if for every material it must be heated above half of the temperature, or so it depends on the material.
Sir, it is depend on the material. More and more literature works are available. So I have also showed some aluminum alloys which are having different temperatures. In different temperatures, we are having different elongations we have obtained. So more and more literatures are available for many materials. Suppose we are doing with new materials like I have done this with aluminum silicon carbide composites, aluminum 6063 alloy. So I have done with the trial and error method. With at 520 degrees centigrade, I got very minimum amount of elongation we have obtained. So maximum I have obtained up to 600 degree, but the components are failed. But at 580 degrees centigrade, we can we get a very good superplastic forming. So this is by the trial and error method. But for some of the many alloys we are having in the literatures, it is available, sir.
Okay, thank you, sir.
Okay. Any other?
Hello, sir.
Yes, sir.
Sir, I have a question. Like, how these secondary phase particles helps in improving the superplasticity? Like, for example, if you take aluminum copper alloy, CuAl2 is a secondary phase particles.
Okay.
So how it will enhance the superplasticity?
Yes, sir. So in the second phase particle, for example, in my case, in the aluminum 6063, it is allied with the magnesium and silica. So this magnesium and silica, while we are heating the component, it will form a Mg2Si, magnesium silicate. This magnesium silicate melting point is somewhat lesser compared to our aluminum alloy. So what will happen at the temperature of more than 550 degrees centigrade? It is nearing to the melting. It is melted. This second phase particles are melted. So it is acting as a lubricant over the grain boundaries. So what is due to the lubrication effect of this, the grain boundaries are sliding one over another. So it is enhancing the superplastic forming.
Okay, in case of aluminum copper alloy also the same
Yes, sir.
thing can happen, sir.
Aluminum, copper. In the copper again, it is the melting point is higher than aluminum. In this case, we
Okay.
have to watch, sir. We have to
Okay.
see that because magnesium and silicate is having magnesium having a less melting point. That is what we are. It is forming the second phase. Suppose some more in the copper, some more alloys are there. Maybe that also enhancing this superplastic formability. It will affect. Suppose it is there means. So depending upon the allying elements, it will be forming, sir.
Okay.
Okay.
Sir, have you done any FE analysis of this superplastic forming?
Yes, we have done through this abacus. Through this abacus, I have done this abacus software, a non-linear analysis. We have given as an inlet of our the UniXL tensile test results. We have given as an input to the input as an input parameter to our ANSYS. Then it is formed. It is we can able to do with this abacus software, sir. I have done this.
Okay, okay. And
Yes, yes, sir.
uh, directly, have you given the stress strain
Stress strain curve value.
values?
Yes, sir. Yes,
Okay.
sir. Stress strain
Okay.
curve values at the hot temperature, hot tensile test. We have
Uh,
already done this hot tensile test. Details are there. During that, we will get the curve. No, that value
yes.
should be implemented during the analysis part.
Okay. At what strain rate you have done, sir, this FE analysis?
The strain rate actually we have done different normally actually in my experiment what I have did with only with the constant strain rate. In my setup I
Okay.
cannot able to change the speed of the UTM machine, so only constant speed only I can, so I have changed only the temperature. So temperature based analysis I have done. So that that report I have taken, and that is given as a input for the ANSYS analysis, sir. That is what I have done.
Okay. Thank you,
Okay,
sir.
okay, right. Any other questions?
Participants, any other questions?
Sir, then we can able to close the session, right? I am very much thankful all the participants for your patience. You are listening for last 1 hour to me. Thank you so much. Maximum what all the things I can able to tell you, that that's what I have given the details. And once again, thank you so much for the coordinators, Taniyachalam sir, for giving me the opportunity.